All right, good morning. So we're going to talk a little bit about UAV manufacturing, and I know that Dr. Marco has already gone over quite a bit in terms of structural arrangements. So we'll have maybe a little bit of review in terms of materials, the manufacturing process, and some high-level description of structural layouts. But then we'll go into some of the details that maybe those of you without much RC experience don't know too much about in terms of how to put together the actual control surfaces and connect servos, and some examples of what that looks like in a little bit more detail in terms of some terminology and things. So first, the materials, and I know there's been a little bit of this already, but traditional stuff has been made primarily of wood. Balsa is one of the most common materials for RC aircraft. It's become maybe a little less popular. But there's some good reasons for that. I mean, balsa is extremely light. So if you just need to get a shape, you don't need a lot of structural strength. Balsa is very good for that. It has some disadvantages in terms of being brittle. Obviously, it's not a very ductile material. When it fails, you get a lot of splinters. So that's perhaps less than ideal, but still has its place, as well as other woods like plywood, where you're layering, and essentially you've got kind of a composite. Yeah, wood itself is already like a composite in that it has different material properties in different directions, and you have to pay attention to things like the grain direction, because along the grain direction you can have a lot more strength than perpendicular to it. And so plywood helps mitigate some of that, and then there are different types of plywood as well in terms of the number of layers, 3-ply versus 5-ply. You get difference in strengths, as well as obviously the thickness. And you can get some very, very thin plywood depending on what you're looking for. Some other common materials, things like spruce or oak or other hardwoods, can be used for some structural elements. Again, if you need something stronger than balsa but don't want to move to something like composites. In terms of metals, it's not really just aluminum and steel, but those are probably the most common. And they both have advantages and disadvantages. Aluminum being a less dense material, maybe it's a little easier to work with, easier to drill through and cut, etc., relative to steel. And it depends on what particular portion of the structure you're looking at as to whether or not that could make sense. And it also depends on the experience of your team. 3D printed materials now become very common as well, and that has a very good place in terms of creating tooling or joints or interfaces, small custom three-dimensional shapes that may not be possible with some other materials, and that can be very quick to prototype and test. A lot of foams are used, however the most common is extruded polystyrene, so that's more of the foam insulation that you would find at the hardware store, and probably the most common is just the pink foam. We've used that many years, and that can be pretty good in terms of something that you can either machine or wire cut into shapes to make for wings or molds for other things. And there's some other styles. Expanded polystyrene tends to be a little less dense, so that has another place. And there are other types of foams that can be available too. In terms of composites, probably the most common is fiberglass. Kevlar has very similar material properties, but different shapes. You get different weaves, and those have different places in terms of how much shape you need to get out of it. So how much structural strength. If you have a very dense weave, it's not going to take three-dimensional shapes very well versus a looser weave. And there's different weights as well. Carbon fiber can also be used, and there's a lot of different sources for carbon fiber out there. In terms of things like just directly buying tubes, one of the most common that's been used in the project in the past, then that's very convenient because tubes are very good in torsion. They're very easy to get a hold of in different sizes and shapes and intersect things. As far as things like carbon fiber skins, you do have to be aware that carbon fiber itself is not amenable to the radio communications. It can block that, so you have to make sure that your antennas are outside of any sort of carbon fiber shape. So if you have maybe a carbon fiber fuselage and you put your radio antenna on the inside, it's not going to work particularly well. There's also some potential restrictions. I know here we had issues a couple of years ago with the environmental health and safety folks in terms of the processes to handle carbon fiber. You get the carbon fiber dust, for instance, is not actually filtered by dust filtration masks. You need either a full dust filtration respirator system, or you use something like a wet sanding process or cutting process for carbon fiber. So different manufacturing processes. I know there have been some examples, but in terms of wood, laser cutter is very convenient, especially for flat pieces. Something that's used many times in the past are these interlocking shapes. So these are multiple pieces of plywood made into a box bar, intersecting joints. Basically, you're designing a three-dimensional puzzle in CAD, and then you get to build it. It's kind of neat. And you can see some of the joints here. I mean, there's files been posted onto the lecture portion on the SharePoint, so you can go and look at that and see some of those interconnections. You can also laser cut, say, holes for different connections between things, which is going to be very, very critical. Water jet can be used to cut flat pieces if you have, say, a more dense material like the aluminum or steel, if you're using that. The CNC foam cutter or router can also be used then. There's the ability to make molds. In this case, we have a female mold or a male mold on the inside, an internal plug that stays there and is wrapped in wrapped in fiberglass, or on the right in Kevlar. And those are some examples that have been used in the past too. When it comes to composites, your result is going to be a direct result of the quality of the tool that you're using. So the better tooling you have, the better your result will be. And it can also be, you can basically make internal tools. So for instance, this box bar here with these laser cut ribs is acting as essentially a jig to line everything up. So things like jigs, either laser cut or 3D printed or machined are very important in terms of making sure that you get the exact geometry that you're looking for. And then this is finished with some sort of vacuum bagging process. You can also use things like a CNC mill or router in order to create different molds. These are female molds. And then I know teams have used in the past some expanding foams, for instance, to then fill that out and then use that as the basis for a shape to wrap in fiberglass or Kevlar or something else. One important thing to keep in mind is that your team itself is going to have a different experience. So go through and come up with a list of what capabilities, what experience your team has, and that can help inform what manufacturing process you actually select for different pieces. It's a very non-unique thing. There's probably thousands of different ways that your UAV could be built with the exact same external geometry. So it's not like there's one manufacturing process that's going to be the best. You just have to pick what you're going to use, and that can involve either the experience that you already have, the capabilities that you have at your various locations, or if you want to learn new processes and kind of expand your capabilities, that's another option. And don't forget about the ability to use the resources at the community college as well in terms of getting them to go through and either route or make molds for you. That's another important capability that we have access to. So when you're coming up with the materials, which are going to be directly tied to the manufacturing process, you also have to think directly about the load paths. So I know that Dr. Marco already talked about what types of loads exist. But you have to make sure that you have structure in place to handle all of the different types of loads that you expect to see. And not all of them will be obvious. You have to think about things like the control surface loads. Right? So if you deflect your control surfaces, that's going to say you deflect your ailerons and now you have a torsional moment, a bending moment on your wing that's in a different axis. Or the motor itself generates both thrust, but there's also going to be a torque component. So whatever the motor is attached to needs to be able to handle the torque, and the torque is going to cause a big jarring anytime you throttle up or down suddenly in particular. And that can be a pretty significant load, and you have to make sure that that's attached to structure that can handle it. And the most important element to think about early on is not just what things are going to be made out of, and not just the path that the load's going to take, but about how you're going to connect things. So if you're making a nice molded fuselage, some sort of fiberglass mold, etc., how are you going to attach the wing to that? How are you going to attach the tail? How does the motor attach? Where does your payload fit within that? How much flexibility do you have in terms of moving elements around? If you lock yourself into a set of geometry and it turns out that your weight and balance is not quite right, then you've got some very serious problems. You're going to have to be scrambling at the end. And we had several teams last year that had some very serious weight and balance problems. So that is not something that can be ignored. And so if you think in terms of how to think about the weight and balance, you've got usually some sort of aft fuselage in your tail, and those are going to weigh a not trivial amount. Usually not that heavy, but they're pretty far away from where your nominal CG would be. So that's a pretty big moment that has to be taken out by something in front of it in terms of either the motor or batteries or payload. And you want to think about, okay, what weight at what distance, and that can help drive exactly how long your nose should be, for an example. So make sure that you start thinking about that sooner rather than later. If you wait too long, it could be the night before a flight test and you find out, oh no, your center of gravity is off by 4 inches. And that has happened, and then people didn't get any sleep trying to fix it. And so better to figure it out sooner rather than later. And those interfaces and connections are very important. So you've got your nice molded fuselage, let's say, where you're going to need some sort of internal substructure to attach the wing to or attach the payload to. If you have a very nice molded shape, you probably don't have a flat spot to put your batteries onto. And how are you going to attach your batteries? Are they going to be zip-tied? Are they going to be attached with Velcro? Or are you going to have just taped on? Tape doesn't stick very well, and if it's, say, a very moist, cool morning with a bunch of dew or something outside. And very cold temperature also makes tape not stick very well. Not that it can't be done. You can wrap around things, etc. But you want to make sure that you have structure to attach each of those things. So all of those internal components are very, very important. So we also care about the overall layout. So in terms of what the load paths are, here's a couple of examples. We've got a very large UAV here, actually a gas motor. So the bending loads, we have carbon fiber tube spar to handle the primary wing bending loads. And that's going into some central box, which is a bunch of laser cut plywood interlocking pieces. Then we've got our tail loads are all going through another square carbon fiber tube that is then attached to this exact same box. We've got a motor mount here for our gas engine, which develops quite a bit of torque and has a bunch of loads on it too, and that is also then attached with a bunch of plywood. And in fact, in the motor mount in this case is fiberglass to make sure that the vibrational loads from the two-stroke gas engine don't vibrate or crack any of the joints. And then the landing gear is also attached to this main plywood box. So basically we've got this kind of central clearinghouse where all of the loads are coming into this big plywood box in the middle. And everything is attached to that in some way. And so that's our central clearinghouse. And we have to figure out, how do we take this apart? Right? So does the tail come off for transport? Do the wings come off? Where do they come off? How are those then put in place? So there's actually a carbon fiber tube that fits inside of another tube. And then some a rotation pin on the back because you need 2 points of attachment. Anytime you have two things attaching, you can't just have a single point unless you want it to rotate. You need a second point as well, and ideally separated as far as possible. So it's very common to have kind of this central fuselage be where all of your loads are coming into. And don't forget your landing loads. So when you come in and impact the ground, that's a pretty significant load. And if, say, your camera is sticking out the bottom of the aircraft, what do you think is going to happen to that camera? Probably nothing good. So make sure that that's not the case. We've had some teams forget about that until second iteration, where they had to redesign where the camera attached, for instance. You also have to be able to grip the aircraft for a hand launch, which means you need something that is human hand sized. So if you have a center fuselage that is, say, 10 inches wide, unless your guy has enormous hands, it's going to be very difficult to actually grip something like that. with one hand. You can do a two-handed thing, but that becomes very, very awkward. And I encourage you to look up some hand-launch videos to see what that looks like. We've got a few in the past. If you don't have any, I took some video from last year's flight demonstration, and I can send you a link to a YouTube video with that. So think about how you actually grip it and where that grip will be. The grip itself should be very, very close to the center of gravity. If it's behind the center of gravity, if you've ever tried to push something in front of the CG, it's going to tend to fall off one direction or the other, so it's not very stable. If it's too far in front of the center of gravity, it's going to want, the tail's going to want to fall back on you, so it's very difficult. So ideally, you have that grip right near where your center of gravity is as well. So another example here on the lower right, we've got another UAV. This actually has a stressed skin. So we have a carbon fiber skin, and so we have very few ribs in this case, with just a little bit of structure to hold everything together, and then the skin itself is handling pretty much all of the loads. Right, so our stress skin can handle the torsion loads and the bending loads pretty easily. It's not necessarily the most efficient, but we don't need the most efficient structural shape to get the weight as low as possible. We want something that's robust enough that we won't have issues in case, say, it rolls across the ground and then hits a rock. You want a little bit of robustness. That's typically a very nice thing to have. So every team's going to have a different manufacturing plan. And by the time you think you have an airplane, it's like, oh, this is looking like an airplane already. You're really only halfway there. Right, so that's something that is very often neglected. All the little attachments, all the details in terms of the control surface, setting up the servos, setting up all your control lines, any sort of covering, if you're going to paint the aircraft, all of those take significant amounts of time. And it can be easily half of it from the point where you think, oh, I'm pretty close to being able to fly. So don't forget about those elements. I've got a YouTube video here. I'm not going to play it right now, but it's a manufacturing time-lapse taken from a design-build fly team back in 2010, showing a manufacturing Thursday, Friday night, and then all day Saturday/Sunday night until like Sunday at 11 a.m. I think we finished, something along those lines. So basically in 3.5 days, an entire airplane from start to finish. And you see that from the time it looks like the airplane, looks like an airplane, it's really only halfway through. So in that, every second is about 5 minutes of real time. So I set up a camera looking down on a table and just manufactured everything on a single table. I actually used a TI-83 to set up a pulse every 5 seconds to take a picture. So really interesting, but we're not going to sit here and watch an 8.5-minute YouTube video. So that's on the PDF, and you can go through and click on that on your own time. So I know a lot of people don't have a lot of experience in terms of what the controls would look like. Basically, these RC aircraft, you buy off-the-shelf servos, and the servos have a small electric motor in them. And they have the little wire going out that goes to your receiver. Your receiver is connected to either your autopilot or to a receiver that transmits to your pilot, who is controlling everything manually. And so this little cable is going out and basically provides both power and then also the signal to cause the servo arm here to rotate. So the arm is attached to that electric motor and rotates. There are different sizes, different torque levels. You can assess the torque levels with things like AVL or XFlow. There's a way to get a hinge moment out of that and then calculate the overall required moment. I would recommend, if anything, oversizing your servos. You don't want to trust that too much. Hinge moment calculations are notoriously unreliable. Even for full-size aircraft, they're plus or minus 50%, and pretty big error bars there, because a lot of it depends on very detailed elements of your control surface that aren't really part of the model. So within that control, we have our servo here. We have the servo arm. The servo arm is then connected to a control horn. The control horn is connected to our control surface. So it doesn't matter what the control surface is. Say this is an aileron. We've got this control horn that is attached. This is an example that shows two different styles. So you can take a piece of wire. In this case, this is steel wire. There's a little special Z-bender that can go in. On the other end, we've got a threaded rod and what's called a clevis that then attaches to our control horn itself, and the control horn is then bolted or screwed into our control surface. So you have to be very careful that these attachments are solid. So this is actually not the greatest example because this just latches on, and really there ought to be a little wire or a little loop going around to keep this from accidentally popping off. So we'll see that in some of the later examples. Your control horn itself has to be attached very securely to the control surface. If it's not and it pulls off, you lose control of your airplane, and we have had that happen, and you lose control of the airplane. And say if it happens to you, your aileron, it's not the end of the world. Right? Hopefully you have a rudder or another aileron and you can still fly. If it happens to your elevator, you're going to end up with some uncontrolled or unscheduled contact with the ground. And it typically does not end well. And we have had this happen. So you have to be very careful that this is attached to something that will not pull off. So one of the things we'll do in our pre-flight inspection is grab onto the control surface, grab onto the control horn, and try and pull it off. Right? Because if we can pull it off on the ground, it'll definitely come off in the air. Right? So that itself is something very important. In this case, we have the hinge line here, and there's a bunch of different styles of hinges that we can talk about. And our controls servo is embedded inside. It could also be on the surface or semi-recessed, and there's many different styles of that. And we'll have a bunch of different examples as we go through. So different styles of Z-bends. You can Z-bend on both ends. It's a little awkward to get them in that case. And this is not actually the straightest of Z-bends. But that's certainly a style that can work. It's better for shorter distances or for control surfaces that don't have a lot of load. And here's a little bit better example. You see a little thicker wire and a shorter attachment. Different hinge styles. There are fabric hinges. These are called CA hinges or cyanoacrylate. That's super glue. So this, you cut a slot into two different wood pieces on either side, and then you put a drop of glue, and the glue wicks through this fabric, which then attaches on both ends. So it's a fabric hinge in this case. So this is not going to be your lowest drag of attachments. It's going to be a little difficult to put that depending on what your materials are made out of. There's also these are called point hinges, and they are different sizes. And here's an example where it's embedded into both the control surface itself and then also into the main wing portion at different levels. And our point of rotation is actually the center of this semicircle. So this is going to be a little lower drag attachment, but these have to be embedded into something that can handle the loads. And if you have multiples of these and they're not aligned properly, your control surface won't rotate. Right? So it's something that may take a little bit of practice to get to work correctly, but can be used to make a little lower drag attachment. So here's another example of that. You see there's a little bit of gap, and it's not quite perfectly centered, but pretty close. So here's another example of a Z-bend on one end with a clevis on the other. Most of these are embedded on the inside. These are a little bit larger. We'll have some other examples. As you can see now the point hinge here, where there's the slot for it to actually rotate through. And this is actually a double hinged, which sounded great in practice, but didn't work, or sounded great in theory, but did not work that great in practice. Excuse me?
How come?
Well, the double hinge, in theory, you basically have a straight portion, and then you bend, and then you bend. So you're turning the flow a little bit more than you could with a single control surface. So in theory, you should be able to get more control surface authority out of it. But what happens is you get a very large increase in the seam hinge moment because you have the double deflection, and the aft part puts a huge moment on to the control surface itself. So the servo has to be very, very large to handle that. So it's not that it can't be done. And there's then an interconnect on both sides to enable them to rotate with a single attachment point rather than having two independent control surfaces.
Yes.
Sure.
So for the servos, do they, I'm not quite sure, so can you control the output of the servo, or is it like a discrete output for each kind of servo that you have?
So can you repeat that?
So like you say you get a servo of a significant capacity for a moment. Can you control how much moment is output, or is it a discrete, or like every servo can only output this much?
Every servo has a maximum rated torque that it can handle, but what you're commanding is a position.
Okay.
And there are different servos that can do different angles, say 90 degrees, so you're getting plus or minus 45, or you can actually get 180-degree servos or even 360-degree servos that will spin forever. Not a good idea in this case, unless you have some sort of other connection between things. But yeah, you're commanding a position, and there's a maximum amount of load that it can handle. And the current draw on your servo is also going to be a function of how much load it sees.
Okay.
So that can either, say you have to put in a big deflection in order to trim out because your wings were slightly twisted and now your ailerons have to be deflected all the time. That means they're going to be sucking down current all the time and thereby helping to drain your batteries. Now, probably the maximum you would really see is something like 1 amp per servo, but that can add up when you have 6 or 8 servos. And that's quite a bit of power. Now, you shouldn't need that most of the time unless you mess up. Well, sure. That's always going to be the case.
Are there any ways or realistic ways to like embed the servo within the wing and not just have like a clean wing with no arms or nothing like all inside the wing?
Yeah, if you have sufficient thickness, it's possible to do that. It's not easy to do. We're doing that on one of our SE advanced ailerons this year to try out.
So how do you actually like control it? Do you just have like a disc like on the axis of rotation for your hinge? Or?
No, the arm itself, imagine your entire servo, including the arm, is embedded inside, and there's a control arm that's going to your control surface. The control horn itself is now, instead of sticking out, it's basically rotated and flipped, and it's now completely on the inside. So I can sketch it out. But
I see, I get what you're saying.
that requires enough thickness, and it depends on having, right, say if you're going to do a foam wing, right, that'd be very difficult to do. Not impossible, but a lot of things here are maybe possible, but then you have to figure out how. How am I going to make this happen? And so it's always very different to theorize and come up with a concept and relative to actually having to build it. So when you have to build it yourself and you've never done it before, usually you should err on the side of caution and things that you know you can do.
Keep it simple.
And keep it simple is a very good general strategy. If you're going to try and do ambitious things, try and keep it to one ambitious thing and not do 3 ambitious things at the same time because that's going to really increase your risk. And for those, maybe go through and do a lot of prototyping to figure out whether or not it'll be possible. So for instance, a team last year wanted to have their propeller rotate around their tail boom. They had a carbon fiber tail boom. They wanted to attach some bearings and rotate the prop around that. And that could happen. They did some 3D printed parts in order to try and get some gearing system together. But it didn't happen in time for the project. They ended up having to come up with a workaround, which barely worked. So another style of hinge is just this piano hinge. We have a single rod going all the way through. This is much larger aircraft, but you can also do very simple, smaller hinges like this. And there are some smaller RC ones that have this. And then you can just do tape. Right? So this is a glider from Tower Hobbies, which you've used just in the past to practice some hand launches. And we have a very simple control surface here where one side, they're basically flat plate, and then a wedge is more or less sanded or cut into one side so that it comes up and butts up against. This is the side where they're directly attached. We have tape going through here. You can barely see the outline of that. And then tape going on the inside as well so it can't just tear off. And you can see this big gap here. Right, so that's probably the simplest, is just tape your control surfaces on. And you can use different types of tape depending on what your materials used are throughout the rest of the aircraft. Right, so that could be embedded on the inside. We've had teams use a Kevlar hinge, where you have basically Kevlar that's embedded inside of your wing and the control surface, and then along the hinge line itself, you put down, say, some petroleum jelly or something to keep any of the glue from getting on the inside of that and keeping it just the fabric itself so it can still rotate about that point. And so that's another possibility in terms of a style of hinge. Servo mount, these are just internal servo mounts. These are very common for RC aircraft where it's just going with this very long control line going all the way back to our control surface. And it's just embedded onto these. These are, I think, spruce sticks here with just screws attached into it. All right, so having some type of wood screw systems is common. We can attach servos in different ways. And here we got our control lines going all the way. It's kind of push-pull system for our rudder, for instance. And here's going back to our elevator with another tape hinge. Right, so they can be mounted on the external portion of the aircraft. So anything you have external is obviously going to increase your drag. So maybe you can make a molding that goes around this, some sort of fairing in order to reduce drag would be a possibility, or try and embed it as much as possible. And that may help reduce your drag. So here we have another push-pull system. The wire itself over this length was not stiff enough, so instead a carbon fiber rod was attached and then lashed on with a bunch of fishing line and glue. So kind of hacked together. And you can actually see how the tail was mounted as well. The tail was built as a separate piece. We got this little L-shaped plate on the aft end of the fuselage and just glued directly in. All right, so you have to think about how your different systems are going to attach in ways like this. So it's been common in the past to use some sort of 3D printed plugs for your tail. Keep in mind that 3D printed material is also very brittle. And so last year we had a team that had their aircraft completely ready to go, and I was very confident. They had center gauge was in the right spot, everything was looking good. And then while walking their airplane out the door to go to the flight test, they bumped their tail on the door, and the 3D printed tail mount broke. Just snapped right off. Right. So there are some unusual load conditions that you could see. You also have to be very, very careful. Right? And maybe when you're taking your aircraft outside at 6 in the morning, after having gotten 3 hours of sleep, right, there's some pretty significant risks involved with that. So don't forget those kind of loads and make sure, ideally, that you could swap parts if you needed. So in that case, the tail was actually glued, or the 3D printed part was glued in. So once it snapped, it was, and they were in a really bad shape. They had to completely 3D print a new one and wait an entire week before they were able to fly. So we can try and flush mount. So we've got embedded inside the wing, in this case attached to a rib. Right? You could also put a big cutout and then put a plate into, say, a foam wing, or if you have another type of surface, embed that partly in, and then we only have the control line out here in the breeze. And that's going to be increasing our drag, a not trivial amount. But again, we could put a fairing around it, and it's not as bad as having the entire servo sticking on the outside. So don't forget about this drag is not trivial. It does add up quite a bit. So if possible, try and do things to reduce that. And it doesn't have to be in place for, say, your glider this semester or any of your initial models. But for an actual service vehicle, you would want to have done everything possible to reduce drag in order to get your endurance numbers or get your top speed numbers, etc. You also should not forget about the wires. These wires have to go all the way to wherever your autopilot or receiver is, right? Which means they need some sort of channel or something to go through, either purely internal or partially external. You don't want them just stuck on the, say, the upper surface, because that's where you're generating your lift. You could cause flow to separate. So if you're going to stick them on the outside, it should be on the lower surface. And ideally, you have something for them to go through, such that, again, you're minimizing drag. So we can also mount our servos in a different direction. So in this case, this is rotating about this axis, causing the control surface to rotate about a different axis, which means that this control attachment itself has to go side to side at the same time. So there is a special linkage, it's called a ball linkage for that, where essentially we've got this plastic housing and then there's a little metal ball in that this screw goes through that attaches to our servo, and that enables it to rotate or go into non-straight directions. Right. So if you have things moving in different planes, this ball linkage is necessary, and there's some other variations on that. Some control horns themselves have a ball linkage built in. So as far as our clevis, we have little bolts going through with a lock nut versus the clamp style, and then usually a piece of fuel tubing or something such that it can't pull out. And then this is what our ball linkage looks like. There are two main sizes, either 440 or 256, both for the threading of the rod as well as for the hole itself. You have different sizes. And so here you can very clearly see this little metal ball and this plastic housing so that it can rotate and go into different directions. The control horns themselves often have a little back plate. So if you're attaching, you have some sort of piece, and then you've got this back plate on the other end where it screws in. You can use something like a wood screw. If you use something like a wood screw here, you want to make sure that it can't just pull out. So if you're going to screw that in, it'd be very common to use something like 5-minute epoxy or something to screw it in first, pull it out, put some epoxy on there so that it can't pull out on its own. Put the epoxy in, re-screw it in, then it's locked into place in a more permanent way. And if your control horn pulls off, your airplane is probably ruined. So it's a very important thing. There are other styles. These are intended just to directly glue in, and this would be suitable only for very small control surfaces. I mean, maybe your rudder would be small enough for that, but probably not. Probably not just glued in, although it's possible to get away with some things you may not expect. And this is a little different style where instead of the ball linkage being on the clevis, it's on the control horn itself. So this is another option that exists out there that we can attach to. All right, so for in this case, we've got our ailerons controlled by a single servo. All right, so we can push pull, and we've got basically a wire sticking out vertically here, goes horizontally on the inside where it can rotate, and then has another 90-degree attachment to go out to the control surface itself so that it can then rotate back and forth as this is pushed forward and back. All right, so with this type of system, you can get away with a single aileron servo. Right, there can be advantages to that. Depends on the size. Depends on the size of your ailerons or other control surface here. And you have to be very exact in terms of how these are attached. So here we have a very small flap to chord ratio, but it's going to be over a very long portion of the span to get a high enough rolling moment. Right, so think about where your control surfaces are going to go. And again, better to have them be bigger than you need than not big enough. If they're bigger than you need, then you just need less control deflection. If they're not big enough, you can fill in the blanks. Right, another external attachment, and then in terms of the, here's an example of a larger scale all carbon fiber wing in terms of what that looks like with our, these are intended for the servo attachments, and then on the inside we have very few ribs, big tube spars, and everything's then attached with a bunch of epoxy. And that has some filler in it. So there's different, they're called microballoons, where you can mix that into your glue in order to make it less dense to fill in gaps without adding a bunch of weight. And so that's another option that exists. So in terms of our spars themselves, tube spars are not the most structurally efficient, but they are extremely convenient. So they don't care about what the direction of. And they're available from many different manufacturers and many different sizes and shapes. And it's very easy to analyze a carbon fiber tube spar in terms of, say, Euler-Bernoulli beam bending theory to figure out what kind of deflections and stresses you would see. So I strongly recommend, if you're using, say, a carbon fiber tube spar and these other sort of carbon fiber spar, that you not size things based on the strength. So if you size things based on the strength required and making sure it doesn't break, you're going to end up with ridiculous deflections. Because carbon fiber, very, very strong material, and you can get huge deflections out of it and still fly. And if it deflects too much, what can happen is your other structure can break. Right? So maybe you could also end up with something like a control surface binding. So if you have a wing and it bends a huge amount and you have ailerons over a large portion of that, and your hinge line makes a big smiley face, are you going to be able to actually move those control surfaces? Right? They're probably going to bind, and that can be a very serious problem. So the rule of thumb we've used in the past is if you look at the semi-span, So you've got an 8-foot wing, 4 feet would be your semi-span. And look at the wingtip deflection, and as long as your wingtip deflection is 10% or less of your semi-span, you end up with a reasonable structure that isn't overly heavy, but isn't going to deflect so much that you end up having control surface binding issues or other skin buckling or other substructure failing. So on your 8-foot wingspan example, that would be something like 5 inches or less of wingtip deflection. And you can assess that pretty easily with an Euler-Bernoulli beam bending theory. Right? So make sure that you're thinking about what materials you're going to use, how you're going to manufacture it, how are all of the different pieces going to come together, and how are you going to control that geometry for the actual assembly process. And so your final assembly, especially in this project where it's going to happen at a different place than where all the manufacturing occurred, you need to control how things attach. And so let's say we have our tube spars here, and they're going to come into some fuselage shape. Well, the fuselage shape, you better very tightly control where these two tube spars fit such that they will fit exactly the same on the wing and onto our fuselage. Because if they don't, if there's an 1/8 of an inch difference, now they don't fit into each other, and now what do? You have to remanufacture one or the other, or come up with some other hack at the very end, where it'd be much easier if you think about it at the very beginning. How am I going to control that? So let's say you laser cut a rib right at the center joint that has the exact shape. So maybe you cut your wing spar holes and they're not quite exactly the right distance apart, but you have this rib and you use the rib as a guide in order to make sure that your tubes fit in such that they'll also fit into your fuselage, right, which is coming from the exact same geometry. Right, so that's a notional example of how to do that. And again, some of the attachments, there's a bunch of other examples in terms of how you can attach your wings on, or you can have clamps, you can have screws, you can tie things on with tape. You can have a button clip system with a bungee cord, like a tent pole type system that pulls everything in. You can attach your wings onto the fuselage and slide in and be held in place with magnets or Velcro, tied together with baling wire. I mean, there's all sorts of options out there. As long as you come up with something that works as a complete system, then you should end up with a successful UAV. So that was maybe a little shorter than I expected. Are there any questions right now? And so every team is thinking about how their pieces are going to fit together, what they're going to be made out of. Yeah.
Actually, I have a question. So generally, how is the wing to body joint done for like these scale aircraft? Do you I assume you make the wing into pieces and then do you attach it on both sides, or do you embed it? Because I saw some pictures over there.
Let's see.
Does it make sense what I'm asking?
So the question is, how is the wing body attachment typically done? And I don't know that there's a typical. Let me see if there's a way I can find. Can people see a whiteboard on here?
Yes.
Well, I mean, obviously we can.
Yeah, now
Okay.
I can see a purple blob.
Yeah, we have there's a purple blob so far. I guess maybe I can change the shape up. Let's say we got our wing, we got some type of fuselage. How is the attachment done? Well, typically you care about transportability, right? So you're not going to keep your entire UAV, which could be, I don't know, 8 feet by 6 feet long, and a single piece, and then fit it into something to transport, right? That'd be enormous. So you want to make it more transportable. Right? So it'd be common to maybe cut your wing into 2 sections, right? That, say we put a split here. Well, now there has to be a way for these to come together and also to attach to the fuselage itself. Right, so those could slide in and out, and let's say you have different sized tubes that come in, or a 3D printed joint, maybe in theory, but I don't know that that'd be the greatest. Or you machine a part that fits together. Right? That's an option. You could also go through and maybe put some sort of rib and then drop that down to the fuselage. You've got a nice flat shape, and then you could screw it in and bolt it in from the side. Your wing could be all one piece and come off, and then they have those two little drop-down ribs and then bolts that go in. Or you could have tabs or magnets. Maybe not the greatest idea, but possible. There's a lot of different ways. We could also instead have a short center section, because that's where the highest bending load exists, and then just these outboard sections become detached. And then these pull off. And then now you think about your bending loads. Right? If you go out further away, your bending load's gone way down.
Yeah.
And here we got Y and some sort of force. This is going to be a force per unit length. Right. So if we push the attachment further out, we reduce the required load. Now, maybe that's not a big deal because we're using tubes that fit inside each other. Maybe this is all some common shape. But all of those would be possibilities. What we can't have is some nice, beautiful molded fuselage and then, okay, nothing to attach it to. I mean, you can't hold things on by magic.
Yeah.
Probably the most common means, or one of the most common means at the RC level is rubber bands. You have basically little tabs on your fuselage in front of and behind the wing, and then you got rubber bands going across, usually making a little X shape over, and obviously that's draggy. But now maybe you got a crash or something, the rubber bands would just snap and your wings would fall off, and hopefully they don't get broken, and maybe something else does. But probably not the most appropriate method for this project, even if it's common. Like, not that you can't do it. There's all sorts of things we could do. It doesn't mean that it's a great idea. And ideally we find a better method that's not as draggy. Okay, so I recommend sketching stuff out, right? When you're talking with your team, or maybe you have an IPT to talk about some of these attachment issues, come up with a whiteboard like this and start sketching things out. If you've got some sort of tablet where you can draw by hand, even better. And it's, I hope this chicken scratch is getting the idea across. Definitely brainstorm this stuff out, and there are many, many ways to do this. The point is you have to come up with how you're going to do it. Right? Not necessarily what's the best, because best is a four-letter word, first of all, literally in this case, but also it depends on what you mean by best. Right? Best as far as the easiest to manufacture, the best load transfer, lightest weight, those are probably not the same.
Good.
Any other questions? Yeah, go ahead.
How do you, and if you have a carbon fiber wing, how do you attach the top and the bottom?
So in terms of what that material looked like before, you could have the wing skins be permanently glued on both sides. And so you have to have enough accessibility to, say, lay down some glue and then attach it. Then you're probably not going to get on the inside again. Or you have access panels.
Yeah.
You can open up
Glue
and
those,
find
screw
things.
those.
Those could be screwed in. They can be taped on. They can
Whatever.
be, I'm throwing all sorts of options out there because I don't want people to get locked into one idea as the only way to do this. Make sure you talk to your advisor, talk to people at your school in terms of how are we going to do this? Do we have the expertise? What resources do we need? But there are many, many ways to do this stuff. Any other questions? All right, so remember at this point in the design process, we should have a sized vehicle. We know how heavy things are going to be, how big our wing is, running through the propulsion, figuring out what motor we're going to use, the size of the propeller, et cetera, the control surface size and the tail sizing using the AVL X-foils, stuff we talked about a couple weeks ago. And don't forget about the weight and balance as well. And all that ties in to this structure. And that's going to close the loop in terms of our preliminary design process. to the point we'll be ready to manufacture things like a prototype pieces and maybe make a glider.